So we have seen a lot of theory. Now it is time for some problems. A 200 volt, 2000 rpm, 10 ampere separately excited DC motor has an armature resistance of 2 ohms. Rated DC voltage is applied to both the armature and field winding of the motor. If the armature draws 5 ampere from the source, the torque developed by the motor is. So what is the very first step that you have to do? First, write down all of the information in a way which is most understandable. Okay. So whenever it comes to DC machines, you will first see whether it is being operated as motor or generator. So here it is a DC motor. So you will first write DC motor and then type of the motor, separately excited. So you will have to draw the separately excited circuit. This is the armature. This is given to a supply VS1, let us say, and the field winding is given to a separate source. We will take this as VS2. Now the back EMF we will take as EB. Okay. So this is the armature current and this is the field current. Okay. Now what is the other information that we have? The voltage, speed and current is given. What is this 200 volts? Is it back EMF or supply voltage? What is it? Whenever it is given in terms of a rating, see it is given a 200 volt, 2000 rpm, 10 ampere DC motor. So that means they are talking about the voltage that is given to it, that it is taking. So it is the supply voltage VS1 and the speed is 2000 rpm. It is given as 2000 rpm. And the current, that means the current that it is drawing. Since it is separately excited, the current that it is drawing is nothing but the armature current. If it is shunt motor, then what will happen? This is the circuit for shunt motor. So this will be the supply current and this will be the armature current. So both are not equal. Okay. Here supply current is the same as armature current. So this is given as 10 amperes. What other information is given? You have armature resistance of 2 ohms. So RA is equal to 2 ohms. This is the armature resistance. The field resistance also you can take as RF. Okay. Next, it is given that rated DC voltage is applied to both armature and field winding. What is the rated DC voltage? Here, this is the rating, 200 volt. Okay. So the same voltage is applied to both field and the armature. So VS2 is also 200. So you can write this is also 200. Next information that we have is the armature draws 5 ampere from source. So this is nothing but the armature current. But we have already here 10 amperes. So what is this and what is 5 amperes? All of this information is the rated conditions. That means if rated voltage is given, then how much will be the rated speed, rated current and everything. Okay. But now there is a separate case. The armature is drawing only 5 amperes, not 10 amperes. In that case, what is the torque developed? So you can write down separately IA2. To differentiate, you will take this as IA1. IA2 is given as 5 amperes. You can take this as case 2 and this is case 1. Case 1 is the rated conditions 1. Now in this condition, what is the torque? This is the question. Now what is the expression for torque? This is equal to K phi into IA. So here since it is separately excited, K into phi is constant. And we know IA. So we have to find this constant. So how do we find this constant? So this can be found from the back EMF. We know that E is equal to K phi into omega. Okay. So if you are taking the speed in terms of omega, then this K and this K are one and the same. If you are taking omega is in radian per second. If you are taking the revolution per minute, then the constant will differ. So whenever you want to find the constant, take this equation, not the revolution per minute. Okay. So this is a very important point. This is where you might do mistakes. Okay. So E is equal to K phi omega. From the rated condition case, you can find out E and you have anyways omega is given in terms of N. So you can find K phi. So you can write from the given rated conditions omega is equal to 2 pi n by 60, right? So 2 pi into 2000 by 60. Then what is E? The back EMF. This is back EMF. So for a DC motor, the back EMF is given by the supply voltage, which is Vs1 minus Ia into Ra. So you can take this as Ia1 to represent the rated condition case. So now we have all of the information. Vs1 is given as 200, Ia1 is given as 10, and the armature resistance is given as 2. So you're going to get 180 volt. So from here you're going to get K phi is equal to EB by omega, which is 180 divided by 2 pi into 2000 by 60. Now this you have to substitute here. So what are you going to get then? T is equal to 180 by 2 pi into 2000 divided by 60 into Ia is given as 5. At 5 amperes we want the torque. So this you're going to get 4.29 Newton meter. Torque unit is Newton meter. The next question, a belt driven DC shunt generator runs at 1500 rpm delivering 10 kilowatt at 220 volt bus bars. The belt breaks, following which the machine operates as a motor drawing 2 kilowatt power. What will be its speed as a motor? The armature and field resistances are 0.25 ohms and 55 ohms respectively. Ignore armature reaction and assume the contact drop at each brush to be 1 volt. So don't worry seeing the big question. Once you write down the information in a concise manner, it will become easy. It will feel simpler. Okay. So what is the main thing here? First, a DC machine was working as a DC generator, and then because of some fault, it starts working as a DC motor. Now while working as DC generator, it has some voltage and current conditions. While working as the DC motor, it will have some other conditions. Okay, so first we will write down what are these conditions. First, it is given that DC shunt generator runs at 1500 rpm. So the speed here is 1500 rpm. And how much power was it delivering? 10 kilowatt. So you can write P output, the output power, which is in the form of electrical power, right? So this will be equal to the terminal voltage, the voltage that it is delivering, into the current that it is delivering, since it is a shunt generator. What will be, how will the shunt generator look like? This is the field winding and the armature circuit. So this is the current that it is delivering. This will be the armature current and this will be the field current. So this you can write as load current. So Vt into IL, this is Vt. Vt into IL is given as 10 kilowatts. What else is given? 220 volt. It is delivering power at 220 volt bus bars. So that means the terminal voltage that it is able to maintain is 220 volt. So these are the conditions when it was working as the DC generator. Now next, what about when it was working as DC motor? It was a belt driven shunt generator. So when the belt breaks, it cannot work as a shunt generator anymore. It will start working as a motor and it will take power from the same source, right? It is still connected to the bus bars. So bus bar is something which will have that voltage. 220 volt bus bar will maintain 220 volt. So the first specification that you can write here is that the terminal voltage is 220 volt. That is not going to change. Next, it is drawing 2 kilowatt power. So that means input power. This will be same, Vt into IL, because this was the generator mode. What will be the motor mode? This circuit is going to remain same. It is now going to draw current. So we will name this as IL1, this is IL2, IA1, IA2. Okay, so accordingly we will write here IL1. This is IL2. Okay, so this input power that it is taking from the bus bar, this is given as 2 kilowatt. Now what is it that we have to find? We have to find the speed. So this we will take N1 when it was working as generator, N2 while it was working as motor. So what is this? N2. Okay, and also we have the armature and field resistances. So you can write that will be same, it will not change, right? So RA is equal to 0.25 ohm and RF is going to be 55 ohm. Another information that we have is that the contact brush drop at each brush is 1 volt. So there will be 2 brushes, right? So this is another thing that will remain same in both the cases. Contact drop at each brush is equal to 1 volt. So now this is essentially like two different cases. In one case speed is given, the other case you have to find speed. Okay. So we use the internal EMF expression. What is the expression for internal EMF? It is K phi n. Okay. If you use omega, then this value of constant will change. Okay. But it will be a constant nevertheless. So now this phi as well is constant. In both the cases, terminal voltage is remaining same. This is Vt and this is Vt, which is equal to 220 volt. And the field resistance is same. So the field current will be same. So the flux is not going to change. So both of this are constant in both the cases. Same in both the cases. Okay. So that means you can write E1 by E2 is equal to N1 by N2. You know N1, you have to find N2. Now E1 and E2 you have to find from the given expression. Okay. So first if you take E1, here it is working as a generator. So for a generator, E1 will be equal to Vt, the terminal voltage, plus the drop across the armature. But in this question, additionally, the contact drop at each brush is given. So then since there will be 2 brushes, you're going to have 2 volt. So this EMF will be equal to all of these voltages. Now here we know Vt, terminal voltage is 220, Ra is given 0.25, this is 2 volt. So we have to find IA1. Okay. So IA1, how you can find the armature current for a DC generator? It will be equal to the field current plus the supply current, IL1, the current that it is supplying. So what will be the field current? The terminal voltage divided by the field resistance plus IL1 is not given. So you have to find from this expression. The output power is given as P out is equal to 10 kilowatt. Okay. So IL1 will be equal to P out by terminal voltage. So this is 220 volt divided by RF is 55 plus output is 10,000 because 10 kilowatt is given divided by 220. So this if you calculate, you're going to get 49.45 amperes. Okay. So here E1 will be equal to 220 plus 49.45 into 0.25 plus 2. So you're going to get 234.36 volt. This is E1. Similarly, you will find E2. This is the case where it is working like a motor. So for the motor, E2 will be equal to the terminal voltage minus the drop across the armature and the brush contact. So this is going to be IA2 into RA minus 2. Okay. Here also similarly you have to find out IA2. Now as it is working as motor, the armature current will be equal to the load, the supply current that it is drawing minus the field current. Okay. So this is equal to, once again IL2 is given in terms of the input power. So IL2 will be P input by Vt. So you write here P input divided by Vt minus Vt by Rf. So this is equal to 2000 divided by 220 minus 220 divided by 55. So if you calculate, you're going to get 5.09 amperes. Okay. So this E2 is equal to 220 minus 5.09 into 0.25 minus 2. This you're going to get 216.72 volt. So now we have E1 and E2. You can find out N1 and 2. So E1 by E2 is equal to N1 by N2. This gives N2 is equal to E2 by E1 into N1. So E2 is 216.72 divided by E1 is 234.36 into N1 is 1500 rpm. So this, if you calculate, you're going to get 1387.14 revolution per minute. The next question is, a shunt connected DC motor operates at its rated terminal voltage. Its no load speed is 200 radian per second. At its rated torque of 500 Newton meter, its speed is 180 radian per second. The motor is used to directly drive a load whose load torque TL depends on its rotational speed omega r in radian per second, such that TL is equal to 2.78 omega r. Find the steady state speed at this load. So first information that we need is it is a shunt connected motor. So you will first draw the diagram for this. Okay. Next you will write whatever information is given. Here it is given its no load speed is 200 radian per second. No load means there will be no torque. So omega is equal to 200 radian per second at t is equal to 0. And the second condition that is given is rated torque of 500 Newton meter. At that torque speed is 180. So omega is equal to 180 radian per second at t is equal to 500 Newton meter. Okay. Next, what is given? The motor is driving a load and the load torque of that load. Okay. So that means the load characteristic is given by this expression. TL is equal to 2.78 omega r. This is the behavior of the load. That means for the load, if there is omega r speed, then it will want a torque of 2.78 omega r. Now we have to find the steady state speed. Okay. So like we have discussed in speed control, there will be electromagnetic torque that will be developed by the motor, and whenever the electromagnetic torque and the load torque, they are differing, then the speed will be varied until it becomes equal to they become equal to each other. So this is the steady state. Okay. But you consider it like this has one kind of graph, this is another kind of graph. So graphically, the point of intersection of both of them will give you the steady state condition. Okay. So that means this is one curve and this is another curve. So this is TL, it is linear, right? And this is electromagnetic torque, it drops with the speed. So now this value will be the steady state value. So you can write here, steady state is the intersection of load characteristics and motor characteristics. Okay, so we will see how to solve this now. Since we have the load characteristic, we need the characteristics for electromagnetic torque. That means how the electromagnetic torque is depending on the speed. If you remember the expression, directly you can write for DC shunt motor what is the expression. Otherwise you can derive. It is simple enough, right? What is E? It is K phi omega. Omega is in radian per second. So from here what will you get? E is equal to, you can take back EMF. So EB by K phi. Now EB, once again it is equal to Vt minus IARA by K phi. Vt by K phi minus the armature current you can represent in terms of torque. So what will it be? T by K phi into Ra divided by K phi. You can write here because torque is equal to K phi into Ia. Remember this constant that you have here, both these constants are equal given that this omega is in, speed is in radian per second. Okay. So you have the expression for electromagnetic torque here. Therefore omega is equal to Vt by K phi minus T by K phi whole square into Ra. Now what we have here is, this is a straight line, right? You can say this is the constant and Ra by K phi square is a constant. So this is a straight line only, right? Now you can see here you have 2 points. Omega is equal to 200 at t is equal to 0. It is 180 at 500. So for a straight line when you have 2 points, then you can easily find out the expression. So what will be the expression? First you write down omega comma t is given by 200 comma 0, this is one point, and another point is 180 comma 500. And if you take this as A and this as B, then omega is equal to A minus B times t, where A and B are constants. If you substitute the first point, then what will you get? 200 is equal to A minus 0. So we have A is equal to 200. This is one equation. And this point if you substitute, then what will you get? 180 is equal to, now A we know, 200 minus 500 into B. From here you are going to get B is equal to 1 by 25. Therefore we have the expression omega is equal to 200 minus t by 25. Okay. Now we have to, this is what electromagnetic torque, and you can take this as the speed, rotational speed. Now this should intersect with the load torque, which is given by 2.78 omega r. Okay. So TL is equal to TR at steady state implies that 200 minus omega r into 25 is equal to 2.78 omega r. So if you solve this, you are going to get omega is equal to 180.18 radian per second.